X26, Maxwell Boltzmann distribution and specific heats. Okay, effective cross-sectional area of two molecules of radii A and B. Two spheres of radius A and radius B. For example, this one is fixed and this one translates. So when they meet, they make a scattering. So it will be bounced in this direction, and this one may recoil to somewhere else. The probability of making a collision is proportional to the cross-sectional area. For example, if this radius is very small, just like point-like particle, then it can see this sphere as a cross-sectional area. That means a pi a squared. When this one is a point particle, this one looks like a circle, so its cross-sectional area is pi b squared. When both of them has non-negligible size, in that case, let's see, this one is radius B, this one is radius A. They can barely making a collision when the straight line connecting the two tangents of this circle meet together. In that case, the perpendicular distance between the two centers of the sphere is A plus B. If the perpendicular distance is greater than A plus B, then it will never hit. If it is if the perpendicular distance is smaller than this, for example, in here, in here, in here, in that case, they can collide. That's the reason why the effective cross-sectional area of two spheres of radii A and B is pi a plus b squared. Okay? N identical particles of cross-sectional area sigma are uniformly distributed in a thin plate. We have a thin plate and a single particle as a cross-sectional area sigma, and there are many of them. Equivalent, uniformly distributed over a thin plate. And this is a fixed target. The volume of this is, we have L square and very thin thickness, dx. So volume is L squared times dx. A single point particle is incident on this target. So when we consider more general case, both of them have non-negligible size, the cross-sectional area will be pi a plus b squared, but because this one is a point particle, so it should be pi a squared. It should be pi a squared, that is a sigma of each. And because there are many of these particles, we need to multiply the number of particles embedded in the target. Okay, to consider that, it is convenient to define the number density. Number density represents the number of particles embedded inside the target per volume. Because it is a thin, very thin, we assume that they do not overlap, and the effective cross-sectional area of all of the particles, target particles, is just simply the number of particles multiplied by each cross-sectional area sigma. The probability of colliding particles, for example, we have a target. Let me give you 10 points here, 5 points, and 0 points, for example. The probability of hitting the target is just proportional to the area, the simplest interpretation. So the area of a specific region divided by the whole region. So the probability of hitting the target is just the total area of the target, total area, sum of these sigmas, divided by the whole complete amount of area, that is L squared. So that is the probability of making a collision of the incident particle. So let me rewrite this one. This one is the area of the target, area of the pure target, divided by the area of the whole plate. Why don't we multiply 1? This is 1. And we know the area of the plate multiplied by the thickness is the volume. This is the volume. Okay. And the number of particles is here and here. And sigma is to be multiplied by dx. We have defined the number density, that is the total number of particles inside a volume. So this should be replaced with small n and sigma dx. All right, so P equals n sigma dx gives us some idea. Probability of hitting the target by an incident particle is proportional to the cross-sectional area of each target, each single target, and it is proportional to the number density. Number density is how many targets are inside the plate within a volume, and multiplied by the thickness. This thickness is parallel to the velocity of the incident particle. So let us continue to study this idea. Why don't we enlarge the depth of the target? So targets are distributed over space, not a single plate, but many plates. And in each plate with the thickness dx, dx is small enough, so they do not overlap. But after increasing dx by 2dx and integrate over the whole region, they can make a multiple collision, for example. So why don't we increase the number of particles? This is a population. Let me call I, and actually this is intensity. I particles are incident on this target, and they will hit the target. As soon as it hits the target, it cannot go further. So as soon as it hits a target with the probability, we say when it makes a collision, then it dies. No collision, it survives. If it survives, then it goes continuously. And then at some point, it will make a collision and it will disappear, and so on. So we expect that the population, initial population, decays smaller and smaller as we increase the thickness of the target. Okay. So probability of making a collision is making a collision. When it makes a collision, the number di, it decreases. So di minus di is a positive. So di, I is divided into I plus di and minus di. And this is positive. Okay, so probability can be obtained by dividing both terms. This is positive and this is positive. This is the probability of making a collision. Probability of making a collision is the same as this. And previously we obtained the probability is the same as the number density, cross-sectional area of a single target, and thickness, infinitesimal thickness. Using this, we can find a differential equation. We multiply I to both sides, then minus di is pi. And then it is expressed in terms of this. All right. Pi. This is 1 minus pi. pi 1 minus pi. What's that? P 1 minus p. It is I. Haha. This is the initial population, and this is a population of making a collision. So it died. Population of not making a collision, it survived. So this amount, 1 minus pi, is population of not making a collision. That means because of this, if we expand this and replace this one with this, population of not making a collision is just a change in population. And we know the change in population is decaying, so di is negative. As a result, we can express this one in this form. Divide both the sides by minus I, then left-hand side becomes di over I, that is differential of log I, and right-hand side is minus n sigma dx, the trivial integral. At the end of the day, we find that population decreases exponentially. This is called the Beer-Lambert law. Let us continue to study this one. Identical particles of cross-sectional area sigma, each are distributed over a thin layer with the number density small n, and a single point particle is incident with the velocity x dot to the target. Now we have velocity. Find the false statement. The decay probability represents the collision probability. Decay means collision. Okay. If it makes a collision in the region, then we need to compute the probability of making a collision. This is the probability of making a collision. The particle must survive until it reaches x. Yes, if it decays in this region, that means until x it survives, no collision. And suddenly, between x plus dx, it makes a collision. Okay? The population, this population is a survival. So it should survive. It should survive I of x. It should survive at x. And then it makes a collision during this process. The collision probability in between x plus dx is this. So what we have to do is the original probability of survival and multiplied by the collision probability. This is collision probability. Collision probability is this, and the survival probability by x. This is a survival by x. This is dies in between x plus dx. Okay. This is the probability of making a collision in the interval x plus dx. Okay, now the integral is trivial. If you integrate x from 0 to infinity, it is a trivial integral of unity. So if we increase the depth of the target to the infinity, then you will find that every incident particle must disappear. If it decreases, then the population decays with exponential n sigma x. So finally, this integral is 1, that means that this is a probability density. Probability density function. Probability density function means if you integrate over all possible values of x, then it must be 1. Now you know how to compute the probability density. Then you'd like to know the average value of the treble before it dies. This one. This one, it is just this multiplied by x integrate over the whole region. Again, x e to the minus x, this integral is a trivial integral. And the final result is 1 over n sigma. This n, small n, number density, can be replaced with the number of particles per volume. This is called mean free path. Average free path. So on the average, particles may survive until this length. For example, you have radioactive material. You want to protect yourself by making use of some target, such as concrete, for example. Then you can estimate the effective depth of this target to protect yourself by making use of this formula. If the cross-section of each particle is greater, then it becomes shorter. If the cross-section is very tiny, it can penetrate longer. If the number density is very large, so dense distribution, then its length decreases. So it is effective to increase the material with larger sigma and larger number density. Then this will may help you. Okay. Now we have finished the collision probability calculation for a fixed target experiment. Now we consider the case two particles are moving. And actually we are considering many particles eventually. if you want to consider a two particle, here it is a molecule, INJ, why don't we compute the average relative velocity? Average relative velocity is just the relative velocity square average. If we expand this, each velocity squared subtracted by the scalar product, expand this, you will find the scalar product of ith molecule and jth molecule. However, the two molecules are independently distributed and they are all randomly distributed. We remember that the velocity average of a single molecule is always a zero, while its square is non-zero. Therefore, this contribution is completely disappeared. Why? In addition, there is no way to distinguish INJ, just like equipartition theorem. We do not distinguish the two values. We assume the two values are the same, and that is the same as this for average over the whole molecules inside the sample. Therefore, if you take the RMS value, square root of this average, we have these two contributions. We have a square root 2 of RMS value of a single molecule. So relative speed of two molecules is exactly the same as a single molecule case, except that there is a proportional factor, square root of 2. Because of this square root of 2, the relative speed is increased by a factor of 2, and the mean free path is decreased by square root of 2. Next, we consider Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution is assuming that this is the origin of the equipartition theorem. It assumes that velocity x2 squared, x3 dot squared, these velocity dependence is just Gaussian form, up to over scale, some alpha, beta, and gamma. And the three dimensions are equivalent, so there is no difference in the over factor. And it assumes the explicit values for velocity of x1 ranges from minus infinity to infinity. The same is true for x2 dot and x3 dot. But we are interested in the speed, average value of the speed. That is our concern. The probability density of the Maxwell-Boltzmann distribution is just obtained by making a product that do not interact each other. Any coordinates dependence are not mixed up. They are completely factorized as a single variable function. So if you multiply them, it is something like mx dot vector squared. And strangely, it is the 1/2 mx dot squared divided by kbt with negative sign on it. This is the kinetic energy of a single molecule, and it is scaled with kbt. Anyway, kbt has the energy scale, and 1/2 mv squared also has the energy scale. So we have additional factor as a Jacobian. This one, it's coming from, for example, in a volume integral in 3 dimension, it is dx, dy, dz from minus infinity to infinity. This one can be reparameterized by using polar coordinates r squared dr to 0 to capital R, and limit r goes to infinity. And for pi, that is a solid angle, the cosine theta -1 to 1, and the phi 0 to 2 pi. So from this, we replace this x vector with velocity vector. Then we have additional velocity squared coming from this Jacobian. The basic idea of a Maxwell-Boltzmann distribution is to respect the equipartition theorem and the central limit theorem. The distribution of the velocity of a molecule inside a large number of molecules should be symmetric. We cannot distinguish the left-hand side and the right-hand side, so negative probability and positive velocity probability should be the same. There should be an even function. So it's the only simplest expression is 1 minus x squared. That is to respect the Gaussian distribution, to respect the central limit theorem. So additional scale factor to make this argument dimensionless is just kbt. And finally, this energy divided by kbt is understood as the Boltzmann factor. In the previous class, we have computed the RMS value for a molecule using ideal gas equation. And this one is exactly reproduced from this model called Maxwell-Boltzmann distribution. Anyway, this distribution integrated over the whole speed of molecule should be normalized to be 1 because it is a well-normalized probability distribution function. Using this, we can do the integration average value of x dot squared. So this one can be computed, and in the text on X26, you will find how to compute this, and the final result is reproducing the result obtained in the previous class. Specifically, this distribution has the maximum value at this one. average speed can also be computed, and that has a factor of 8. And divided by pi in the denominator. Here, the distribution changes illustrate the dependence of the temperature at T and at lower temperature and higher temperature. The width of the distribution varies. This is a speed. Colder, so average value of the speed must decrease at lower temperature. For example, at T equals exactly 0, then it should fall down as a sharp peak at absolute 0. Area is invariant. This area, probability density, so this area should be 1. Value of speed that gives the maximum value is proportional to square root of T. That can be derived from this one. RMS speed increases as T increases. RMS is here, somewhere around here. RMS increases as temperature increases. Maximum value of probability, this probability density increases as T decreases. Next, we consider, until now, we have considered a molecule that does not have any structure in it. So we have considered the translational kinetic energy only. However, if a molecule has a structure, then it can make a rotation, and the rotational kinetic energy may contribute to the internal energy. Therefore, the specific heat of gas depends on the structure. First, monatomic gas, such as helium, neon, argon, krypton, xenon, radon, they are all single atom. Its molecule is made of a single atom. So we can treat it as a point particle, although it is not equivalent to mathematical point. Relatively, it can be approximated as a point particle, so that cannot rotate. Even though it rotates, it does not contribute to the rotational kinetic energy at all. So XYZ axis rotational inertia must vanish. If a molecule has a pin structure, it is allowed when diatomic gas hydrogen, nitrogen, and all of these have two molecule atom. If you rotate this one along this axis, rotational kinetic energy doesn't contribute. However, if you rotate this one about this axis, it has non-vanishing rotational inertia. This is wrong. I1, I2, they are the same. Here, another axis, I1, I2, I3. So I3 must be 0. This is wrong. This is a 0. If you have polyatomic gas, for example, 3 atoms or more, in that case, for example, in a plate, triangular structure, 3 atoms, in that case, any axis, rotation about any 3 axes has all non-vanishing rotational inertia. Therefore, in that case, 3 axes contribute to the rotational kinetic energy. Once constituents of a single molecule form a plane, then all 3 components of rotational kinetic energy inertia survive. That's correct. Just like what we have done with the translational kinetic energy, we can equally apply the equipartition theorem. If every rotational inertia is not vanishing, then mv squared, I omega squared, they are all equivalently kBt. So monatomic gas has three kinetic energies, 3 independent axes of translational kinetic energy. So its kinetic energy is 1/2 mv squared style. So each axis will give 1/2 kBt, and we have 3 axes of translation. That's the reason why internal energy of a single molecule is 3/2 n kBt. And the rotational inertia I1, I2, I3 are all 0 for monatomic gas that is structureless. There is no rotational kinetic energy contribute. In a diatomic gas, this one is a 0, diatomic gas, this one is 0, and this one is a non-zero. So we have 3/2 kBt for the translational kinetic energy, and 2 times 1/2 kBt for the two independent axes of rotation that carries non-vanishing rotational inertia. That's the reason why the internal energy of diatomic gas and diatomic gas is, instead of 3/2, it is 5/2 of n kBt. In polyatomic gas with greater than 3, we have all three axes of rotation allowed. Therefore, 3½ kBt for the translational kinetic energy and another 3½ kBt for the rotational kinetic energy. So it is 3 kBt. For a single molecule, if you have n molecules, all right, the heat capacity, CV, at constant volume is now understood in terms of the equipartition theorem, considering both translational and rotational kinetic energy. By definition, change in internal energy is CV multiplied by temperature change. If volume doesn't change, the gas does not work. Therefore, the first law of thermodynamics gives delta Q is the same as delta internal energy. And delta internal energy is by definition CV delta T. Now, if we consider monatomic gas, internal energy is 3 times 1/2 NKBT. Now CV can be read off from the internal energy formula by taking the derivative with respect to T. This trivial derivative will give CV 3 times 1/2 NKB. For the diatomic molecules, we have internal energy formula 5 times 1/2 NKBT, and we take the time derivative, the temperature derivative, CV is 5 times 1/2 NKB. For polyatomic gas molecules, it is 3 NKB. All right. Adiabatic process. Adiabatic process does not involve any heat transfer. So internal energy change can be inferred from the work by putting negative sign on it. From this, temperature change is the work, infinitesimal work, minus divided by CV. Ideal gas law is the same for any kinds, for example, monatomic, diatomic, polyatomic, always PV equals NKBT. We take the differential of this, and this is P times V's differential, so PdV plus VdP. And right side is NKB dt. NKB dt, using this formula, if we substitute this one, NKB minus CV PdV. And we have PdV on both sides. So we combine these two. PdV, VdP, and right-hand side, combine these two. Then we will find that gamma, that is Cp over Cv. VDP is the same. This side is just P minus plus C plus Cv and Kb, right? dV. Okay. Find the false statement regarding adiabatic expansion. Again, adiabatic dq equals 0. PdV plus VdP is this one. And again, gamma appears many times. Cp is a constant pressure. Cp over Cv. From this expression, we can rewrite this one into this. Divide both sides by PB, then it becomes this one appears in the denominator, this one appears in the denominator. So we have this, and both of them are log. As a result, is a log gamma, log V gamma, and log P. If we combine both of them, it gives PV gamma is a constant. PV equals constant is a constant temperature, but PV gamma is constant is specific for the adiabatic process. In an adiabatic process, changes its volume and pressure in this form. We can make use of the invariance of PV gamma. Invariance of PV gamma to find all of these formulas. So it looks complicated, but for example, PV equals NKBT is true always. So NKBT wait a second. I think this part is unnecessary. What we need is only this formula. PV gamma equals P1 V1 gamma equals P2 V2 gamma, something like that. If we choose V1 only, then we can find P over P1 equals V1 over V gamma. Okay, that's this. That's this. We don't require this. It should be raised. And this is a trivial replacement. The work done by the gas during an adiabatic process can be computed. Work done by the gas should be PDV integral. And PDV integral can be expressed in terms of these formulas. For example, this one, P dV equals P1 V1 over V gamma, right? So P1 times V1 gamma is factored out, and V to the gamma in the denominator, dV, right? And this integral is carried out after carrying out this definite integral. We can obtain this. I think this one is unnecessary, and this one is enough. During this calculation, we need to remember Cp minus Cv. The constant volume, the system does not work. Constant pressure is always greater than constant volume. That amount is NKB. That's quite important. So we have to memorize this. And for a more specific case, if you carry out some little algebra, then gamma minus 1 over gamma can be expressed in this one. That application can be applied to compute this. And you can do this job. 14. The work done by the gas consists of n molecules, is P delta V. Isobaric process, pressure is the same, so it can be included inside. So PV is always the same as NKBT, and NKB is a constant, so it is to be replaced with NKB delta T. Constant pressure. Heat is Cp delta T to a gas sample. The heat capacity Cp at a constant pressure satisfies the condition. Delta Q is a Cp delta T, and this is a Cv delta T plus PDV. P delta V in constant pressure is NKB delta T, right? That's the reason why Cp delta T and Cv delta T has this difference, and from this, Cp minus Cv is NKB. That has been used in this expression. So monatomic gas, internal energy is 3 times 1/2 NKBT, and from this, by taking the temperature derivative, Cv is read off in here, and Cp is always Cv plus NKB. So just add NKB in here to find it 5 times 1/2 NKBT. Diatomic gas, internal energy is 5 times 1/2. CV has 5 times 1/2. And CP is just a sum of CB and NKB. So 7. Polyatomic gas, internal energy is 3 NKBT, and if you add NKB, it is 4 NKB for the constant pressure. In free expansion, the gas is in equilibrium only at its initial and final states. Right. During the free expansion, pressure, volume are not defined. The intermediate states are not defined well because they are not in a thermal equilibrium state, right? Because delta internal energy is 0, temperature is invariant. Yes. According to gas equation, PV equals nRT, PV equals constant. The relation holds only in a thermal equilibrium state. That's right. The work done by the gas, so this equation can be applicable only in the initial and final states. The work done by the gas during a free expansion is 0. If you applied action and reaction, vacuum does not apply any force to the gas. Therefore, the free expansion does not require any work.